modeling and its pitfalls. So far we have learned about dimensional homogeneity and the Part11 method, using power products for converting a homogeneous physical relation to dimensionless form. This is straightforward mathematically, but certain engineering difficulties need to be discussed. First, we have more or less taken for granted that the variables that affect the process can be listed and analyzed. Actually, selection of the important variable requires considerable judgment and experience. Selecting a selection of the important variables requires considerable judgment and experience. The engineer must decide, for example, whether viscosity can be neglected. Are there significant temperature effects? Is surface tension important? What about wall roughness? Each pie group that is retained increases the expense and effort required. Judgment in selected variables will come through practice and maturity. This course should provide some of the necessary experience. One of the variables are selected and the dimensional analysis is performed. Once the variables are selected and the dimensional analysis is performed, the experimenter seeks to achieve similarity between model tested and prototype to be designed. With sufficient testing, the model data will reveal the desired dimensionless function between variables with pi functions. For example, a function of with this equation available in chart, graphical or analytical form, we are in a position to inject complete similarity between model and prototype. A formal statement will be followed as I said, the formal statement is flow conditions for a model test are completely similar if all relevant dimensionless parameters have the same corresponding values for the model and the prototype. The prototype, it is the formal statement for modeling. Formal statement for modeling. This follows mathematically from the previous equation that we can write the relation, for example, pi1 prototype equals to pi1 model, and other dimensionless products should be equals in prototype and model. Instead of complete similarity, the engineering literature speaks of particular type of similarity, the most common being geometric, kinematic, dynamic, and thermal. Similarity, we have example, we can write kinematic, dynamics, thermal, similarity, and geometric. The first similarity that will be discussed is geometric similarity. Geometric similarity concerns the length dimension L, the main dimension, and must be injured before any sensible model testing can be proceeded. A formal definition is for the geometric similarity is a model and prototype are geometrically similar if and only if all body dimensions in all three coordinates have the same linear scale ratio. Note that all length scale must be the same. It is as if you took a photograph of the prototype and reduced it or enlarged it until they fitted the size of the model. If the model is to be made 1/10 the prototype size, its length, width, and height must be each be 1/10 as large. Not only that, but also in entire shape must be 1/10 as large. And technically we speak of homologous point. So all dimensions in model should be have a relation to all dimensions in prototype. And all shape also should be similar to in model to all shape in the prototype. With these two conditions, we can say we have homologous point. Which are points that have the same relevant relative location. For example, the nose of the prototype in homologous. For example, the nose of the prototype is homologous to the nose of the model. The left wingtip of the prototype is homologous to the left wingtip of the model. For example, the geometric similarity requires that all homologous points be related by the same linear scale ratio. All homologous points be related by the same linear scale ratio. Linear scale ratio. This applies to the fluid geometry as well as the model geometry. So we have another statement for the geometric similarity. All angles are preserved in geometric similarity. All angles are preserved in geometric similarity. All flow directions are preserved the orientation of model and prototype of model and prototype with respect to the surrounding must be identical. For an example, this figure illustrates a prototyping and a 1/10 scale model. The model lengths are all 1/10 as large, but its angle of attack with respect to the free stream is the same for both model and prototype, 10 degree and 1 degree. So the lengths are 1/10 and the angles are same to a stream, in this case 1 degree and 10 degree and 1 degree. All physical details on the model must be scaled, and some are rather subtle and sometimes overlooked. So we have for notes for the model nose radius might be 1/10 as large. Must be 1/10 as large. Second, the model surface roughness must be 1/10 as large. And the three, if the prototype has a 5 mm boundary layer, for example, if the prototype has a 5 mm boundary layer trip, wire 1.5 mm from the leading edge, the model should have a, for example, should have a 1.5 mm trip wire and $1,500 from its leading edge. And the last one for this example is 4. If the prototype is constructed with producing fastener, with protruding fastener, the model should have homogeneous protruding fastener 1/10 as large. the model should have homologous one-tenth as log. And so on. Any departure from this detail is a violation of geometric similarity and must be justified by experimental comparison to show that the prototype behavior was not significantly affected by the discrepancy.